Okay, so to start things off, we'll have a review of your concept in MEC30, your statics of rigid bodies, which is method of joints and method of sections. Okay, first of all, let's have an intro. So a blank is a structure composed of members fastened together in such a way as to resist change in shape. What's the answer? What is that blank? Correct, Janelle and Julia. So Flores and Santa Maria. And Julia. Yeah, it's truss. Okay. So since it resists, yeah, type lang. By the way, for recitation, please type out your answers in the chat so that it's easier to give you a point. Okay. So once again, by definition, truss resists change in shape. So what kind of body resists deformation or change in shape? Can anybody give me what kind of body or what kind of structure is that? Deformation is negligible, doesn't deform. From your MEC30. Very good. Julia and Rom. So Solomon and the Lacus. Julia. The Lacus. Rom, Ian, Nicola. Oh, you're not here. Okay. Right. Late and Rolly. Okay. Right. So correct, it's a rigid body. Recall from your MEC30, rigid bodies are bodies that resist deformation. Okay. So within that, we have three general assumptions for simple trusses. First is that their joints behave as smooth pins. So in actual, members of a truss are joined together by means of pins at their ends or riveting or welding to a gusset plate. Now, even though that's the case, if due care is taken to assemble the bars so that the center lines of the members intersect in a common point at each joint, the forces in the members may be calculated as if they were pin connected, even though their ends are actually riveted or welded to a gusset plate. Okay? So for the purpose of computation, we assume joints are always connected by smooth pins. Next, all loads are applied at joints. So trusses are constructed so that all applied loads act at the ends of the members. So recall, once again, from your MEC30 statics, if a member is experiencing bending, meaning there's load throughout its body, not at the end, therefore your structure now is a frame, not a truss. That's why for trusses, loads are at joints. In relation to that, weights of members are negligible because weight acts at the center of an object. And if that's the case, the center of a member is half its length. Therefore, that weight would create bending. And once again, bending is considered in frames, not in trusses. That's why weights for trusses of members are negligible. Okay? Now let's talk about its free body diagram. So a free body diagram of a typical member of a truss would show it acted upon by two equal, oppositely directed forces exerted by the pins at its ends. For example, we have this truss right here. Let me show you. Recall. Okay. Let me just zoom in. So let's say I have this kind of truss, right? We know that if I analyze this, let's say I take this member, isolate it, the forces present for this member would be this way. We have two forces acting on each member, keeping it in equilibrium. For this case, it's most likely compression force from method of joints. Okay, so this kind of member is called a two-forced member. This is important later on, and I'll show you why once again later on. Just know, okay, each member of a truss is held in place by two forces, keeping it in equilibrium. Okay. Next, so I've mentioned method of joints, so now we'll tackle that topic as a review method of joints. So recall, method of joints only involves concurrent force systems. To solve for method of joints, you're going to select a joint with no more than two unknown forces involved. So for us to be reminded of how to solve, let's have an example. Number one, determine the forces in the members of the roof truss shown using method of joints. Okay, let's solve. Number one. Okay, so we're just doing method of joints. Step one, for a truss like this, I need to find out the reactions, right? So let's choose react, or let's indicate our reactions. We have a roller here. Remember, for rollers, there's only one reaction, which is perpendicular to the surface. Therefore, it's something like this. Okay, let's call that your RA, reaction at point A. We have a pin here. Pins have two reactions, two supports, one vertical, one horizontal, one parallel to the surface, one perpendicular to the surface. So let's note all of the directions I'm giving here are assumptions. Later on, we'll find out if my assumption is correct. RA is upward. Let's call this RDV for vertical reaction as upward as well. And then I'm going to guess or assume horizontal reaction as this at this pin is to the left. So let's call this RDH. Okay. Now that I've denoted my reactions, next step is to solve for them. So remember, one of the first things to do to solve for reactions is to use moment. Recall we have three equilibrium equations, right? Moment, Fx, and Fy. So usually for this, we start with moment. Next step, choose which point you'll take your moment on. So you can choose point B or point A, up to you, whichever you prefer. Let's try taking moment at point A. Okay, so summation of moment at A equals 0. RA passes through A. Recall, whenever a force passes through the moment center or the point in question, it doesn't create moment. So moment is 0, so just ignore that. Next, we have 192. Next, figure out if it's clockwise or counterclockwise. So to me, okay, clockwise is positive. Counterclockwise is negative. Okay, your professor, past professor, or from some books you've read, might say the opposite. Okay, so this is arbitrary, meaning there's no right or wrong way to say which one is positive or negative. But for our course, for our section, train yourselves now. Clockwise moment is positive, counterclockwise moment is negative. Okay. So now let's figure out, is 192 clockwise or counterclockwise about point A? What I'd like to do is try to rotate it, and as you can see, it's definitely clockwise. So that's positive. So positive 192, then take perpendicular distance from A. So this is your force, this is the perpendicular distance equal to 8. So that's 8. Next, 96. If you extend the line of action of 96, you'll see that it passes through point A as well. Once again, any force that passes through your point in question does not have moment or does not produce moment. So that's 0. So ignoring that. Next, you have RDV. RDV, I assume to be upward, so rotate that about A. It's counterclockwise, so that would be negative. So negative RDV. Take the perpendicular distance, so 8 plus 8, that's 16. Next, RDH. RDH, if I extend this line of action, once again, it passes through point A. Therefore, this does not create moment, so ignoring that. So this all my equation, equate that to 0. From this, I can solve for RDV. Please solve. What's the answer? Correct, it's 96. Correct, Beatrice and John, Aragua and Pascual. Wow. Okay. It's 96. Unit, as you can see, we're in kilonewtons. Positive answer, therefore my assumption for the direction of RDV is correct. It is indeed upward. Okay, now I have first reaction. Next, let's figure out the other reactions. We have done moment, so next we would use Fx or Fy. Let's start with Fx. Summation of forces X equals 0. Okay, let's look for forces X. We have this 96 to the right, therefore positive. What else? We have this RDH assumed to be to the left, so that's negative. RDH, there's no other forces along the x-axis or horizontal forces. Equate that to 0. And then from this, I can directly solve for RDH, which is 96 kilonewtons. Positive, therefore correct assumption to the left. And then lastly, try using summation of forces y equals 0. Okay. Then you can solve for RA. So RA assumed to be upward, so positive. RA, 192 downward, therefore minus 192, and then plus RDV. There's no other vertical force, so equate that to 0. RDV is 96. Knowing that, please solve what's the value of RA. Correct, Beatrice and Janelle. So Flores and Pascual. It's 96. Okay, 2 points. Recall for those who already got 2 points, refrain from chatting for a while. You may answer if no one else is answering. Okay, now that you've got your reactions, you can now choose where you'd like to start your method of joins. You can either start at A or start at B. I like starting at the left. So let's start at A. Okay. Next step would be to draw free body diagram. So this is your point A. We have reaction here, so draw that. That's your RA. Next, make intelligent guesses on the direction of your force in member AB and AC. So how do I make an intelligent guess? Recall, all joints should be in equilibrium. I have a force upward here. To put this in equilibrium, I need a counteracting force downward. And I can get that from member AB. Okay? So this is your member AB. Let's call that F, force in member AB, FAB. Once again, this is upward. Counter that. I'll make this downward. Another thing, this force is to the left. So I need another force to the right to counter that. And I'll get that from AC. So FAC should be to the right. Okay? So far, these are all guesses. You'll see in your solution if you're correct. Okay? But most likely this will be correct because you made an intelligent guess. So now let's solve. You'll use your equilibrium equations, Fy or Fx. So let's start with summation of forces y equals 0. So first, FAB to the left, therefore negative. FAB, next step, I need to get its y component. So how? Going back to our truss, okay, this is your FAB. I'm given dimensions of angle. So I'm going to use slope to solve for that. Okay, so let's draw that. So this is 8, 6. I can just copy that, 8, 6. Get the hypotenuse, square root of 8 squared plus 6 squared is 10, right? Therefore, this is 10. So now I have the slope of my member AB. To get the horizontal or vertical component, choose the vertical leg over its hypotenuse. So 6 over 10. Okay. So force times, once again, this is also 6, 8, 10. 6, 8, 10. To get the vertical component, choose the leg. That's also vertical. So once again, that's 6. So multiplied by 6 over hypotenuse 10. So that's how you get the vertical component when you're given slope. Next, we have RA, upward, so plus RA. There is no other vertical force, so equate that to 0. Considering RA is 96, please solve what's FAB. Correct, it's 160. Positive, right? Correct, Jason and Jade, De La Cruz, and Longito. Jade, Longito. It's 160. 160 unit kilonewtons. And then positive, therefore correct assumption. Recall when it's towards your point, it's compression. If it's away from your point, that's tension. FAB was assumed to be towards the point, positive, therefore correct assumption. So that is compression. Okay, so that's my first answer. Next, let's continue to get effects. Okay, FAB to the left, therefore negative. Negative FAB. Once again, now we have to get the x component. So take the leg that's parallel to the x-axis, or take the leg that's horizontal. So it's this. So that's 8. So multiplied by 8 over hypotenuse, which is again 10. Okay, next we have FAC to the right, so that's positive FAC. There's no more forces that are horizontal, so equate that to 0. FAB is 160. Please solve what's FAC. Correct, it's 128. Russell and Jason. Mondragon, hello. 2 points. Mondragon. Team. It's 128. 128 kilonewton, positive. Therefore, my assumption is correct. It's away from the point, so that's tension. Okay. I'm done with point A. Now, you have to choose which point next. Recall, we have a rule that there's only 2 unknowns per joint. So therefore, you can either use B or C, because FAB is done, FAC is done. If I choose C, only 2 unknowns, right? If I choose B, also only 2 unknowns. So up to you, which one you prefer. Okay, you can start with either. Let's try B. So at B. Let me move things. Yeah. Okay. At B. Okay. For late enrollees, don't worry, I'll just update my class list as we go. Alright, so let's isolate B. This is point B. You have to transfer forces. For example, here, FAB is compression. So if you draw FAB here as well, Okay, it should also be in compression. So towards the point, that's your F, A, B. Next, we also have other forces. So FAB, next FBD is your FPG. Make an intelligent guess to get its direction. This is upwards to the right. I need a force to the left to counter that. And I can get a force to the left from FBD. Therefore, I'll choose this as the direction so that it's to the left. Both of my forces upward, therefore I need a force downward. So I'm going to take it from here, your force BC. Okay, next, take the slope. This is still FAB, so this still has the slope 6, 8, 10. Or you can use 3, 4, 5 as well. That's the same. If you divide everything by 2 here, you'll get 3, 4, 5. You can use that as well. But I'll just keep it as is. Okay. Now, how about FBD? As you can see, FBD also has base 8, height 6, so there's also 10. The same thing here, base 8, height 6, 10. Now, you can already solve this. You can either use symmetry, right? Since FAB, since this figure is symmetrical, right? Left equals right side. So by symmetry, okay, FBD is equal to FAB, which is equal to 160. Okay. Or you can just solve it again by using summation of forces x. Okay. So if you're not confident with your assumption, you can still solve for it. Summation of forces x equals 0. Let's start. This is to the right, therefore positive, FAB. Get the x component. So that's the horizontal leg, so times 8 over 10. Next, this is to the left. So minus FBD. Take the horizontal component. So once again, that's 8 over 10. There's no other horizontal force, so equate that to 0. Knowing that FAB is 160, if you solve for FBD, you should get 160 as well. FBD 160 positive. Therefore, correct assumption. FBD is towards the point, therefore that's compression. Okay. Next, to get FBC, we can use summation of forces y or vertical equals 0. FAB is upward, therefore positive FAB. Vertical component, so vertical leg, that's 6, so 6 over 10. Next, FBC is downward, so minus FBC. Next, FBD is also upward, so positive FBD. Once again, take its vertical leg, which is 6 over 10, and equate that to 0. FAB is 160, FBD is also 160. Please solve what's FBC. Correct, it's 192. Correct, Tim and Gian. So, Pangilinan and Mondragon. Points. Right? So 192. Positive, therefore correct assumption once again. It's away from the point, therefore that's tension. Okay? So I've solved for 4 members now. I've gotten this and this. So the remaining member now is FCB. Now you can either isolate B, isolate C to solve for FCB. Okay, up to you. To me, the easier choice would be at C. Okay, so let's solve at C. So isolating that, and then we also have, this is an external force, 192. We have another force here, 96. Then internal forces for each member. So FAC is in tension, so I have to draw it in tension here as well. So away from the point, FAC. Next, FBC. BC is tension as well, so I have to draw it that way, so away from the point. This is my FBC. And then now we're just gonna guess what direction FCD is. I'm just gonna assume it's tension. Okay, so FCD, and that's what we're looking for. So to solve for that, we can just use summation of forces. So summation of forces X equals 0. Negative FAC, since to the left, both to the right, so positive 96 plus FCD equals 0. Knowing that FAC is 128, please solve what's FCD. Correct, it's 32. Correct, John and Jade, Paragua and Lomiba. How? Paragua, Lomiba. Okay, 2 points. 32. Positive, therefore correct assumption, it's away from the point. So once again, that's tension. Now you've solved for all of the members. You can now solve as well for Fy, just to check, got the same answer. If you solve for Fy, again, this is just to check. FBC is upward, 192 is downward, 0, therefore FBC equals 192, which is correct. Okay, so this is just to check. Right, that is an example for method of joints. Any questions for method of joints? Please answer in the chat. Question or none. Okay, no questions. So let's move on to the next topic, which is method of sections. By the way, if you have any questions, you may use your mic. Perhaps. Okay, method of sections. Once again, this is a review. So as a review, method of sections involves non-concurrent force system, in contrast to your method of joints. And its rule is you're not supposed to cut more than 3 members of the truss. Once again, to familiarize ourselves with the concept, let's have an example. Okay. Determine the force in members BC, CE, and EF. So BC, CE, EF. We have this. Okay. So we're looking for BC, CE, EF. Okay. Now you're gonna cut where you want to find out the forces in the members. So essentially, I'm gonna cut here. And then it's just 3 members, so it's allowed. So I'm gonna cut this way, right? After cutting, you're gonna isolate either the left or right side. If you isolate the left side, there won't be any external forces. However, you have your reactions. If you isolate the right side, you have external forces, and once again, your reaction. So this is just up to you, whichever you want to solve for. Okay. To me, let's try solving the right side. So I'm gonna isolate the right portion of this figure. Okay. Since I'm gonna isolate the right side, I need to find out the reaction at D. So let's solve reaction at D. Okay, let's call that RB. I'm assuming it's upward. Again, these are just assumptions. So to solve for RD, I'm gonna take moment on the other support. Okay, so at A. So summation of moment at A equals 0. Start. Since we're taking moment here, I'm just gonna ignore all the reactions here. But for your info, there's gonna be vertical and horizontal reactions. Okay, I'm just ignoring it since that's where I'm taking my moment. Okay, next 50. Rotate it at A. That's clockwise, therefore positive 50. And then get its distance. So that's 1 plus 1. Next, 80. Rotate it about A again. That's clockwise. Once again, it's positive. So plus 80, perpendicular distance. We can extend the line of action of this. Okay. And then this is the perpendicular distance, which is equal to 0.75. So times 0.75. What else? We have RD. Rotate RD about A. That's counterclockwise. So minus RD. Perpendicular distance, that's this length. So that's 1, 2, 3. There's no other force, so equate that to 0. Please solve what's RD. Correct, Ronel and Audrey. So Manrique and Juano. Manrique, Juano. Ron. Okay. That's 53.33. So 53.33 unit kilonewton. Positive, therefore correct assumption, it is indeed upward. Okay, so now that I have that, I can now isolate this. Mhm. Yeah. So I don't know how your previous professors did it, but for me, whenever I isolate method of sections, I like to assume all forces to be in tension. Okay, that's just more convenient for me. We can do it another way. That's fine. Okay, so this is force in member BC. What else? This is force in member CE. And then this is EF. Okay. Now the technique here is to find a point where two of the three unknown forces intersect. So looking at this drawing, at what point do two of the forces intersect? In here. What point? Do two of the three forces intersect? Two unknown forces intersect. Okay, correct, Beatrice and Janelle, so Pascual and Flores. Since you only answered, I'll give it to you. It's C, not F. Look at C. FBC and FCE passes through it if you extend their lines of action. Okay? So if I take moment at that point, FBC and FCE will cancel out. So let's do that. Summation of moment at C equals 0. And we're only considering this drawing, okay? Once again, FBC, FEC passes through it, ignore it. 80 kilonewtons also pass through it, so ignore that, as well as 50, okay? So now we're left with FEF. So FEF rotated about C, that's clockwise, therefore positive FEF. Next, perpendicular distance. This is the perpendicular distance of FEF to C, and that is also equal to 0.75. So this is 0.75. Next, what else? Okay, RD, rotate that about C. That's also, that's counterclockwise, so that's negative RD, perpendicular distance, so extend the line of action of RD. This is the perpendicular distance to C, which is equal to 1. So RD times 1. Considering RD is 53.33, by the way, if you haven't already, try to store this value. Okay, I urge you to store values like this so that our answers are uniform. So using the stored value of RD here, weight that to 0, I can solve for FEF. Please solve what's FEF. Correct, it's 71.11. Correct. Edwin and Sierra. So Mira and Gutierrez. Mira. Okay. It's positive 71.11. Okay. Positive, therefore correct assumption. It's away from the point, away from the member, therefore that's in tension. Okay. Next. Now the problem here is how to solve for FCE and FBC. One way is to take moment again. If you look at the original drawing, if you take moment at E, FEF and FCE intersects that. If I do summation of moment at E equals 0, I can solve for FBC. Okay, that's one way. You may try and do that. Another way is just to take summation of forces vertical and horizontal equals 0. Let's try vertical. So summation of forces y equals 0. Okay. FCE is downward, therefore negative FCE. Next, I need to get the vertical component of that. So we get the vertical component. Let's look at CE. This is your CE. Okay, let's look at the slope. Base is 1, height is 0.75. Okay, and then to get the hypotenuse, that's just square root of 1 squared plus 0.75 squared, and you should get 1.25. Okay, so transfer that to our drawing. This is 1, 0.75, 1.25. Okay, to get the vertical component, just take the leg that's also vertical, so that's 0.75, so multiply it by 0.75 over hypotenuse, 1.25. Next, let's look at other vertical forces. We have 50 downward, so minus 50. Else, we have RD. RD positive, therefore upward, therefore positive. There's no other vertical force, right? So equate that to 0. Please solve what's FCE. Correct, Elika and Trinity. 5.56. So Daoud and like 5.56. Positive, therefore correct assumption. Don't forget the unit kilonewton. I assumed CE to be away from the point, so that's tension. And then lastly, to get FBC, you can just, again, you can use moment, or you can just use summation of forces x equals 0. Okay. FBC to the left, so negative FBC. FCE also to the left, so negative FCE. Take its horizontal component. So horizontal leg is 1. So 1 over hypotenuse, 1.25. What else? We have 80 to the right, so plus 80. And that's, we have FEF to the left, so minus FEF equals 0. FEF is 71.11, FCE is 5.56. Once again, I urge you to store these values. And then storing that, you can solve for FBC. What's the answer? Yeah, it's 4.44, correct. If you stored the value. We got it first. Trinity and Edwin. Davao, Alala, Mira. Davao, Mira. Yeah. Okay. So it is 4.44 positive, therefore correct assumption. Newton, tension. Now, in the event that you get a negative answer, that just means your direction is incorrect, but your value is correct. So let's say I assume this to be compression. If I assume that as compression, I'm going to get a negative answer. Then you just have to note that it's not compression, it should be tension. Okay, that's it. That's all you have to do if it's negative. Right? That's method of sections. Any questions for method of sections, please answer in the chat. Okay, since you don't have any questions, that ends our review for method of sections and joints.